Previously, we discussed the steepest descent method. A modification of steepest descent method, which is known as Newton method, is also there to solve for unconstrained optimization problems and multiple variable optimization problem. Okay, so let's look into some concepts that are needed for us to understand before we can use the Newton's method. I want to repeat, the Newton's method for multiple variable is essentially a modified version of the Newton's-Raphson method for a single variable optimization problem that we have discussed in the previous lecture. Okay, so what is the Newton's method? If you recall, right, it derived from the Taylor series expansion, right? We have this kind of expansion. Now we are doing an expansion not with respect to a single variable, but with respect to a vector, and that's why instead of the single variable that you saw in the lecture last class, we have a vector notation, and this is what we can do, right? So typically we, neglect the higher order terms, and from there we can, basically derive different expansion series, and we can have del fx, del xy, and this is the equation that we will get. If we set, this portion to 0, okay, what we get is we have this del fx, and then we have del y equal to 0, okay. Then we reach this equation, which is Ct plus Hy. And what is this Ct and Hy? I will discuss that in a little bit. But essentially, we will arrive at this equation that we need to solve. And from this equation, we can get the value of y. And this y is essentially the search direction, right? Instead of the steepest direction, descent direction, this is also a direction that you need to be moving your solution into, okay? And that is what is used in Newton's method. Okay, so the delta x is given by this approach. Okay, so we are delta x is xk plus 1 minus xk. So we can, from this, we can essentially, rewrite this equation, and we can have the iterative equation that is used in the Newton's method. So a couple of things that I want to discuss. We gave, the marble rolling down the hill analogy, right? And that algorithm, or the steepest descent algorithm, essentially focuses on the steepest descent direction. One of the things that Newton method does is it actually uses the steepest descent direction for sure, but in addition to that, geometrically, it also computes what is known as the curvature of that surface at a given specific location. And it uses that information in addition to the steepest descent direction algorithm to guide where we should be moving. And having a curvature information on top of just the first derivative information is useful, and that is what is being used in the Newton's methods. And that's why you have this H inverse, which is essentially computed with what is known as Hessian, and the Hessian has the curvature information of the surface that is being used in this overall algorithm that we have. So it's a slightly modified and adapted version. It's a, sort of a step up than the steepest gradient method that we have. Okay, and again, as I said, you can assume at least for the Newton's method, alpha is assumed to be equal to 1. So the step size is fixed, and it is always kept as 1. Okay, so from there we get this search direction, which is dk, which is minus H inverse Ct. Okay, and this is the equation that we use to solve for this class of problem. So again, I will show the utility and the steps that are used by the Newton method with a specific example, and all of this will crystallize it. But the key thing that I want you to understand that this is sort of an advanced version of steepest descent method, where the Hessian information or the curvature information of the surface is also used along with the steepest descent direction to find out the search direction in which we should be moving. Yep. So in order for us to understand, the algorithm and the working of the algorithm, we need to have the concept of the gradient, which actually I have already discussed with the steepest descent direction. So if you're given a function, we can take a derivative of that function with the number of variables that we have, and that will be a vector. If we add up all of these vectors, we will essentially get a resultant vector, and that resultant vector is essentially the gradient of fx at x, right? Okay, so for example, if we have two variable function which is given by x1 and x2, I can take the two derivative with respect to x1 and x2, and this will be essentially the equation for the gradient of the function fx with variables x1 and x2. Okay, this is an example that you can try, And again, if you want to evaluate and sample this function at a specific location, for example at 1 1, what happens when x1 is equal to 1, x2 equal to 1, which is the case here, then what you do, you take this function and you substitute x1 equal to 1, x2 equal to 1, and you put that in this equation, and from there you will get a vector which is here, which is a vector at a specific location in the landscape of the function that we are interested in. So that's concept one, which we have already developed for the gradient descent algorithm. And remember what we need to do in the gradient descent, we need to move exactly in the opposite direction. So we will take a negative of this, and that will become 1, 1, and that's the direction we need to move on. But in the Newton's method, one more information is actually used, and which is the concept of Hessian, which is the second derivative that we need to take. And this, as I said, if you take the landscape, the Hessian is essentially, the way to think is measuring the curvature of the surface at that location, where the gradient is like the steepest or descent or the descent direction that that we measure, but this measures the curvature of the information. So how this is computed? So Hessian matrix for a given function looks like this. So you will be computing the second derivative, which is del x del 1, del x del 2, and del x del n with respect if you have n number of variables. And similarly, you will be computing all this element of this vector and that all the elements of this matrix, and that will be used in the overall computation to solve for this overall problem. Okay. So the Hessian of the matrix is symmetric. That's one of the property that we have, right? And let's try to see how we can compute the Hessian with a specific example problem. Okay. So if we have this function x, which is function of x1 and x2, these two are here, I can create a Hessian, and it will have essentially 4 elements. The Hessian matrix will have 4 elements, which is del square fx divided by del x del 1, del square del fx divided by del x del x2, and so on, which is listed here. And what we can do is we can take this component which is essentially defined by this equation. So we take the del x1, which we have computed in the last slide, which came out, which at least we can take this one and take the first derivative of that will be here, and then take another derivative with respect to del x1, and it will come out to be 2. Similarly, we can compute all the other elements, right? And then once we compute all this element, this will come out to be 2, 0, 0, 4. Now note, specifically in this case, this Hessian matrix is not a function of x1 and x2, and it is going to be constant irrespective of whatever the location of x is. If this still had x1 and x2 inside, then it will be a function of x. But it turns out, at least since this is a quadratic equation, and if you take the derivative, second derivative, you come to a situation where the Hessian matrix is not function of the variables itself. So at each location in the landscape, this Hessian will be essentially fixed. And that's why, even though we will be moving from iteration x1 to x2 different location, the Hessian is not going to change for this problem. But that is not necessarily true for other problem. Depending upon which problem, what the function is, this might be dependent on x1, x2, and so on, or it might not be dependent on x1 and x2, and so on. Okay. So we have covered all the concepts, and we have also discussed like the main equation that is used in the Newton's method. Now let's take a specific example problem and see how the iterative scheme of the Newton method could be used to solve for unconstrained multiple variable problems.